All right, gang, MATH6500. As with both videos that I am posting here lately, I'm getting um, uh, interrupted quite a bit. So I already have the notes written out, and see no reason to reinvent the wheel. So I'm just going to go over this with you. Kind of cool. We're shifting gears from assessing normality of our errors, residuals, and switching gears to constant error variance. And one of the ways that we can take a look at that is a very kind of a clever, very simple procedure, actually, called the Brown-Forsyth test that you see commonly reported when assessing constant error variance assumption. And the thing I like about, well, let me pump the brakes a little bit. If we go back a little bit and think about assessing normality, I thought it was kind of cool that we could use chi-square goodness of fit test, a test arguably that a lot of undergrad students see in their introductory statistics class, right? So by looking at or comparing the actual counts to the theoretical counts of what we would expect if we had a normal distribution, again, knowing that we have the 68, 95, 99.7% rule, which gives us the proportions that we get from, one standard deviation above the mean and two, and so on and so forth. So I thought it was really cool that we use such a simple statistical technique to examine something, a little bit more sophisticated. Well, that's the theme here. The Brown-Forsyth test is nothing more than a version of Levine's test. Now, if you've taken 6610 from me, we studied ANOVA, and ANOVA is just a glorified t-test. For example, if we are assessing the difference between two means, mu1 equal mu2, then we'll probably use an unpooled t-test, unpooled two-sample t-test. But if we get into multiple means, more than means, 3, 4, 5, whatever it may be, k can be anything greater than 2, then we use ANOVA techniques. Well, from your study of ANOVA, you should have been taught, if you took 6610, you were taught, that one of the assumptions is equal variances. So to test the assumption of equal variances, we often use Levine's test. And Levine's test just uses deviations from the group means and creates a very clever process. Brown-Forsyth is just a modified Levine's test where instead of looking at the deviation from the group means, it examines the deviation from the group medians. So arguably, we end up with a test that is more robust. Now, in using Brown-Forsyth test to examine constant error variance, the logic behind the test is if the error variance is increasing or decreasing, but let's just think about focusing the narrative on increasing. Across X, then the variance in one group will be different. Actually, the variance in the second group will be larger than the first group, again, if we have an increasing error variance than another group. So I think that would probably be better if I drew a picture. So let's just assume that we don't have equal variance. And if you don't have equal variance, you often get this, fanning out. So let's just fill this in with a bunch of dots. Okay? So if we examine the variance from, say, this x compared to, say, this x, well, if we don't have constant variance, then we can reasonably assume that the variance in this part, again, we have increasing variance here, is going to be larger than in this part. Now, what's the process? The process is kind of clever actually. What we do is we come in and we divide our sample into preferably 2 equal parts. It doesn't have to be equal, it just needs to be close. Obviously, if we have an odd data set, we can't get it equal. But anyway, we want it to be very close. We'll define n to be the sum of n1 plus n2, where n1 is the sample size from group 1 and n2 is the sample size from group 2. So what's the logic here? We come in and we try to cut this right in the center. We look at the median of the residuals for group 1. We look at those deviations. We get an average. We compare, let's say the median here is not 0. We look at these deviations, get an average, and because we have an increasing pattern, it is reasonable to think when we put this under the test of a 2-sample t-test that the average deviation over here is going to be greater than the average deviation over here in the context of the null hypothesis for a 2-sample t-test where we have mu1 equal mu2. For this diagram, it would be much more believable that the mean of the deviations for group 1 is going to be less than the deviations for group 2. So for this drawing, I would expect us to get a p-value less than 0.05, where we would reject the null and assume that the means are different, and therefore we don't have constant error variance. So that's kind of the logic behind the test. So once we make this division, again, trying to get n1 and n2 pretty close, we calculate the absolute deviations of the residuals around the median for each group. All right, so it's the median of each group of residuals, not the grand median. We calculate a test statistic, which I'll give you in just a second, conduct a 2-sample t-test, and of course if we get a statistically significant result, we cannot conclude constant error variance. And I'll write that up much more clearly, I think, on the next page. So let's let E sub I1 denote the ith residual in group 1, and E sub I2, of course, denote the ith residual in group 2. We'll calculate the deviations from the median. So DI1 will be calculated by taking the absolute value of the residuals, the errors, minus the median of just those residuals. We're not taking the median of all the residuals. So that creates kind of a caveat in R that drove me crazy for a couple of minutes, and I realized that I had to take a couple of extra steps to address that. All right, so kind of drum roll please here. We have our test statistic is calculated by taking the mean of the D1s minus the mean of the D2s divided by the standard error. Standard error is just the square root of 1 over n1 plus 1 over n2 times s. The variance, where we'll get s, right, we'll take calculate this value and take the square root of it, is the sum of the deviations squared plus the sum of the deviations squared over degrees of freedom n minus 2. It turns out that this test statistic follows a t-distribution degrees of freedom n minus 2 under the null hypothesis that the error terms have constant variance versus the error terms do not have constant variance. And we'll test that, of course, at alpha equal 0.05. Now, let's get out of here. Shoot, I thought I already had this up. Daggone it. Sorry, guys. Slacking on the job. All right, so you can see that we have x and y, and the very first thing I want to use, or I want to do, is I want to create my model, and that's just y from x, and then I'd need a summary of the model. Now, I need this right here. I need my model, so I'm going to write this down so I can say that. I'll tell you what I want to do. Let's do this. All right, perfect. All right, so what I want to do is I want to write my model down here. So the model is going to be y hat equal 54.682. Plus 0.626 times x. All right, so I'm going to need that in just a second. All right. I want R to be just a little bigger. All right, now I don't want to create my residuals yet, because if I create my residuals from this model, then I'm going to have 55 residuals, and for some reason when I create my subsets, even though x and y will be subsetted, any calculations I make from x and y are not subsetted. It's kind of strange. I would demonstrate it, but I don't want to take up precious time demonstrating that. So anyway, the first thing I would do is let's find out where we want to make our cuts. So I would probably just look at the range of x. So it ranges from 20 to 59, and I'm just going to look at the median of x, and it is 40. So it kind of makes sense to me without doing a lot of work. I'm probably not going to get it I'm going to run group 1 from 20 to 39. And I'm going to run group 2 from 40 to 59. Now, as you should know, just because we have a width of 19 and a width of 19, it doesn't mean that my sample sizes are going to be equal or even close to equal. I could have a skewed distribution. Clearly you could have disproportionate group of cases. But you know what? Just for demonstration purposes, that'd be something that'd be easy to figure out. Just for demonstration purposes, I'm going to go with the 20 to 39 and 40 to 59. All right. So first thing I need to do is I need to, let's just create group 1, and I'm going to do that by subsetting my data, and I want to choose my x's less than 40, and I'm going to do group 2, and I'm going to subset data, and I'm going to choose my x's greater than 39. So I don't get into the less than or equal to stuff, so this will take care of things. All right, so let's attach group 1 and start working with it. All right, so we mask a few of the variables, x and y. Now, the very first thing I have to do is I need to create my residuals for the model. So I'm going to create the residuals for group 1. And of course, our residuals are our observed values, which will be my y, minus the predicted, and the predicted are going to be 54.682 plus 0.626 times x. All right. So now, if we go back to first thing we need to do is we need to create our deviations. So I'm going to create this as a DI1, and I'm going to do the absolute value of the residuals minus the median of the residuals. Now I need, again, just the residuals of group 1 compared to the median of only the residuals of group 1. All right? Now, next thing I need to do is start thinking about, for group 1, what do I need? Well, I need the mean of the deviations of the D1s. So let's go ahead and get those. So 4.087. I need the sample size. So let's see what the length of, well, let's just look at the length of x's, it'll do it. So it turns out that we ended up with 26 here. So that means that I'm going to have 29 over here because I know there's 55. Of course, obviously the mean of the deviations, I have to get that from group 2. So here I'm going to need the deviation squared, so the d sub I is minus the mean of the deviations for squared, and I'll need the sum of that. So let's just do the squared deviations for group 1. So I need di1 minus the mean of di1, and I need those squared. And then I need the sum of the squared deviations 1. So 282.034. And I know down here I'm going to have, of course, 53. Now everything else I need to get from group 2. So I'm going to detach group 1. And I'm going to attach group 2. So the first thing I need to do, it's kind of cool that I've already done this before, so what I need to do now is I'm just going to go up and get the things that I've done previously. So I'm going to call this, obviously, resid 2. And still do my x's. And I'm going to go up and I'm going to get the deviations 2. So then I'm going to need the mean of my di2s, so 8.625. All right. So we're going to have a negative test statistic, which is legal. All right. Let's go up and get squared deviations 2. di2, d12. So 984.742. All right. Now, looks like to me we have everything that we need to be able to make the calculations. Let me grab another sheet of paper. Well, I don't have another sheet of paper. All right, so let's calculate s squared first. So calculate the variance. So we have 282.034 minus 984.742. Should be a plus. Got tunnel vision on this up here. Over 53. So let me grab my calculator. Now, if I didn't make any silly typos in my calculator, I get 23.9. So the standard deviation is 4.889. All right, so now we're going to look at our test statistic. So we have 4.087 minus 8.625 over 4.889. So 1 over 26 plus 1 over 29. All right, so should have already had this. Sorry, guys. Hate it when this happens. I'm too deep into the video to stop. And on the bottom, I get approximately 1.32. So it looks like the test statistic is negative 4.538 divided by 1.32. So it's approximately negative 3.438. Now, what does this tell us in terms of calculating the, how we can get rid of that now, calculating the p-value. So what this tells us is, first of all, we can just think of all this. You know, we have approximately a t-distribution, degrees of freedom n minus 2. So we're working with the t-distribution, degrees of freedom 53. So for this t-distribution, we need the area to the left right, times 2, because this area equally likely. Well, very easy to do. So just we want the area, so PT, negative 3.438, degrees of freedom 53, multiplied by 2. So we get p-value very close to 0.0011, which says we have a level of statistical significance at the 0.01 level. So looking back at the null and alternative hypotheses, we would reject the null. Hate to get all dramatic here and draw a line through it, but that's what we would do, and conclude that the sample data leads us to believe that the error terms do not have constant variance. Now let's go back, let's detach group number 2, and then let's go back and attach just our data, our main data where we have everything. Let me just make sure everything's there, 55, yeah. So now let's create our model. Well, we've already done that, haven't we? Yeah. So let's just take a look at our plot of our fitted over our model. And already sit over our model. And when we do that, I think it's pretty clear why we rejected the null of equal variance, constant variance, because you know, we have the classic fanning out shape of the residuals, don't we? So I think that the results of the Brown Foresight test gives us a lot of important information about the constant variance assumption. Because I tell you, it would be, I've done this a long time. I hate to play that card, but it is what it is. I've just been teaching stats for many, many, many years. So many times we can look at that and think, well, yeah, it kind of looks like a shotgun blast, and go on with using a linear model to describe the relationship between X and Y. When, although we didn't violate the normality assumption, it does look like up here that the constant variance assumption has been violated. All right, gang, that's all I got. I will encourage you to. Well, I'll just show you. You can tune out if you want, but I do want to show you how if I create the residuals from the model, and then I do a, let's just call it group 1A for the second time, and I do a subset of my data with X less than, what was it, 29 or 30? I forget. No, I think it was 40. Whatever. And I attach, let me detach data, attach group 1A. Now, if I do length of my X, you'll see that I get 26, and my length of my Y I get. But if I do my length of the residuals, notice I get 55. So I wonder, when I first started working on this, that all my calculations for the residuals turned out to be the same for group 1 and group 2. But I found out through R that if you make a calculation with the values from the initial data set, that even though, for example, I don't know why I'm beating a dead horse here, but if I do group 1, group A, well, if I create a new data frame, it will actually show the residuals just for group 1 and A, so, or 1A. So kind of confusing. So I just found it easier back here to just create the residual manually, if you will, just for the X's and Y's that are in each group, respective group, group 1, group 2. All right, sorry about that. That was a tangent. You probably toned out and didn't listen to it anyway, but if you did, thanks for hanging around. All right, take care.